5? 75. 7. Oh, oh my goodness, so much work. Okay, let's check this out. The idea behind it seems pretty straightforward. Tangent line to an equation at a point, so point slope form. We got the point, we don't have the slope, we find the derivative and plug in the point. However, this one, actually, oh no, arctan y. Yeah, we're going to do implicit differentiation. Super.
Could you replace arctan y with tan x?
No, because then you're assuming that arctan y equals x, but we don't know that. Alright, so let's check this out. Derivative of x squared is 2x. That's easy enough. When you do the derivative of this term, don't forget product rule. So, first times derivative of the second, plus the second times derivative of the first, which would be 1. And then there's derivative of y, and derivative of -1 is 0. So, any questions just on this line right here? Now, you could have solved for dy dx and then plugged in. I just chose to plug in at this point, whichever one you prefer. So all the x's are going to be negative pi over 4. All the y's are going to be 1. So 2x will become negative pi over 2. If y is 1, this becomes 1/2, so that's right there. Oh, there's the x. And dy dx. And then arctan y is arctan 1, and so there it is. I'm just plugging in. And then there's, I went ahead and just simplified, well, not really simplified, but multiplied those two together, and arctan of 1 is pi over 4. And so now it's getting a little simpler looking. I'm getting ready, I think, to solve for dy dx. But let me make sure everybody's okay with getting to this point. All right, what did I do next? Oh, I combine my like terms, and then I start solving for dy dx. And so I finally get dy dx is this. So there's my slope, there's my point, and then point slope form. And I really could have left my answer this way. That would have been fine. Any questions at all? Any other questions? Luca! 8-9? 8-9. Ooh, that's a big number. Oh my God, a word problem? Man. All right, an airplane flies at an altitude of 5 miles. So we have that. Toward a point directly over an observer. So there's the observer and there's the plane flying in that direction. Consider theta, and x is shown in the figure. So they must have given us this figure. So for part A, when they say write theta as a function of x, that means make an equation with theta and x that says theta equals, and on the other side you can only have x. So looking at this triangle, we have opposite and adjacent. So tan theta is opposite over adjacent. And then solving for theta, we get this. So any questions there? They're pretty straightforward at that point. But then, oh, it looks like it might be related rates. Well, I don't know. Let's see. The speed of the plane is 400 miles per hour. Find d theta dt when x is 10 and x equals 10 miles and x equals 3 miles. So they want us to do this problem twice, but it's really not that big a deal once we figure out how to do it once. So if the speed of the plane is 400 miles per hour, that's going to be the change of x with respect to time. Because the plane is flying in this path, which is basically the same path as x. So they gave us dx dt, and because that distance is going to shrink, that's why this is a negative speed, or negative velocity, I should say. And then from part A, we have this. So if you take the derivative, oh, I was doing the derivative in a different way the year I did this. But if you take the derivative with respect to time the way we did it, here I'll go ahead and redo this one. So starting with theta equals arc tan 5 over x, we can say d theta dt equals And then the derivative of arctan is 1 over 1 plus the ratio squared. But then we have to do chain rule. So we have to do times the derivative of 5 over x. So that would be negative 5 over x squared. And then also chain rule implicit differentiation times dx dt. So any questions how I got this? Which essentially should be what I end up with down here. So this will be equivalent to this when you get rid of the complex fraction and stuff. So, and then I've just plugged in dx dt as negative 400. And so then once you get here, then it's pretty straightforward because you're just letting x equal 3 or x equals 10. So the key was the implicit differentiation part, related rates. Any questions about that? Any other questions? Oh my God, related rates is coming back. It's like we can't forget anything. Well, can I have your homework then? And we do have a little reality check. Take one glance over those formulas because you're probably going to have to know them. Going out on a limb here. Bum, 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 bum.
Thank you very much. Very upset because I don't know what they are.
That's always positive. Oh, yeah, yeah.
Yeah, and I'd love to have them say what's great about it, but that's too long.
All the codes are negative.
So I have them say like, hey, cosine, cosecant. Oh, yeah.
All right.
Down, don't turn them over. I'm gonna give you guys. No way.
Yes, I asked you. You saw me. I would have opened my English folder, tried to put it in, but I felt like you guys didn't know I had to sign up with this.
You're welcome. Thank you. You're welcome.
Yeah, I have friends that do that.
What?
So people get on it.
Inside. Everybody's here. That's so exciting.
You tell them what? Oh, that music is not that good. I'm just the museum makes it expensive.
All right. Does everybody have one? Not everybody has one. All right, then you may begin. So there's number 1. Any questions about number 1? Are you ready for number 2? There's number 2. So, no calculus yet. And then, of course, I screwed up on the calculus. Right? I don't know. That might mean I have to put one of these on next time's reality check.
That's what I did.
All right. Any questions on number 2? Here's what number 3 should have been, which is none of the above. So, not even close to any of them. So, any questions? Yes. Yeah. Any other questions? Yes, Trey. Uh-huh. Hypotenuses, hypotenusi, I don't know. A hypotenuse is always positive. And so this forces it to always be positive. Any other questions? All right. Well, then, let's take some notes. Right there. So I believe that this is it. This is the day that we learn the last of our integration formulas. Dun, dun, dun. Now, it obviously doesn't mean we're not going to learn nothing new. Wait, is that too many negatives? We're not going to learn nothing new. So we are going to learn new stuff. Yeah, that's okay, right? Oh, the English language sometimes. Oh. So today we are going to spend the time talking about inverse trig still, but this time integration. And we're actually going to spend 2 days on this section, not because integration specifically to inverse trig is that hard, but you're going to see with our last few problems that we have in the notes, when we start mixing things together, this is where the true art of integration comes in, of trying to figure out what to use when. So, but before we do this, I want to quickly remind ourselves about the derivatives. So you guys take a moment, try to remind yourselves, what is the derivative of arc sine u? What is the derivative of arc tan u? And what is the derivative of arc secant u? Take a moment to fill those in. I'm going to have that erased. I don't know if any of you have ever gone back and watched the videos, and then when I have the screen frozen, I can't freeze it on the recording without just pausing, which I usually don't do, so they can see all the stuff that I'm doing behind the scenes. It's not very exciting, but it's like, anyway. While you guys are writing them down, somebody raise your hand. Remind me, what is the derivative of arc sine u? Anybody remember? I know somebody in here remembers. Rena! Well done. Yay! And then we know the derivative of arc cosine will be this negative. All right, what about the derivative of arctan of u? Sufrith.
U times after 150.
Excellent. And then the derivative of arc cotangent is that, but negative. And to bring it on home, the derivative of arc secant u. Rena. Exactly. Well done. So we're just going to do this backwards. Except it's going to look a little different. I mean, we could exactly do this backwards. But we're just going to... I'm not going to take the time. This is going to be one of those few attempts. I'm not going to take the time to derive the formulas for you. But they're going to look slightly different than just going backwards. So, are you ready? Are you ready? Here we are. There they are. These are the formulas for the integrals. Let me make that a little bigger so that you can definitely see that. And I believe, if memory serves, that this will be the last of our just basic integration formulas. So I'll give you a second to write them down, but then we'll take a look at them. I'm looking around at everybody's desk and I see like so many pencil cases and pouches and things out. I think there's two things that say a lot about a person. What they choose to put in their pencil case and what shows up on their YouTube feed. Anybody in here not have a pencil case? See right there, that says a lot. No, I'm just kidding, I'm making that. I don't know what it says. If you've never used a pencil case, I actually did not use a pencil case until, I don't know, 10 years ago? Pretty recent in life. They're awesome. Where have I been? I don't know. If you've never used one, give it a shot. They're quite convenient. And then go to Daiso and try to just have fun what you're going to put in it. All right. I know some of you guys are still writing these down, but let's just take a look. So I know it may seem like I've left something off of the arc sign. Why do the other two have the 1 over a in front, but the arc sign doesn't? It really doesn't. And the best way to convince you guys that I don't want to take the time in class to do this, but if anybody wants to do it on their own, or we can do it later, if you take the derivative of these right-hand sides, you will see it works out to give you the integrand. It really does. And then you'll kind of see why the arc sign doesn't get the 1 over a, but the other two do. The other thing is, you may have noticed the arc secant, the absolute value. Now, with the absolute value, I'm going to put a little note here. This absolute value at the integrand, we actually usually don't have it. So I'm going to put a little note here that this formula works Oh. Huh. That this formula works even when there is no absolute value in the integrand. But we always need this absolute value in the answer. Get out of the way here. In fact, most often you'll actually see the formula written without the absolute value on the integrand. And that is another one where, trust me, that's the way it is. If we were to do the derivative of the right-hand side, you can see that it works out, but just kind of go with it. It's just not worth taking the class time for it. Then, the last thing is, notice I don't have anything here with arc cosine or arc cotangent or arc cosecant. Yes, let's just pick the second one for example. If this was the integral of the negative du of a squared plus, or du over a squared plus u squared, then yes, you could say that the answer is 1 over a arc cotangent u over a plus c. But we usually don't do that. We usually just say it's negative arc tan. But yeah, you could, and it would still be okay. But when you're looking for multiple choice answers, don't do that. Because the answer is probably like 99% of the time not going to be there. We just use these three. But, you know, if it was a definite integral and you're evaluating, it would still work. The last thing, just kind of keep an eye on this. Because it's like, wait, how do I know when to use which one? Because notice it's a squared. It's not just a 1. But here's the thing. A is a constant. So it's easy to spot, if you know it's going to be one of these three, it's easy to spot arctan, because arctan is the only one without the square root. And then when you're looking at the difference between arcsine and arcsecant, your first instinct might be that, well, arcsecant has something outside the square root, and arcsine doesn't. But you're going to find that that's not always true. It just kind of depends on du and all of that good stuff. So don't let that be your clue. Instead, look at what's inside the radical. For arcsecant, it's u squared minus a squared, and for arcsine, it's a squared minus u squared. Arcsecant is the variable minus the constant. Arcsine is the constant minus the variable. That's your clue. That's how you know when to use which one. Don't pay any attention to that thing. I don't know if I have an example today that turns out to be an arcsecant where you don't have something outside the radical, but it just does happen. Trust me, it does. So that shouldn't be your clue. Instead, look at the order of what's inside the radical. Now, I know there's questions, but so actually I'm not even going to ask if there's any questions. Let's just do an example, and then I'll see if there's questions. But does everybody have these formulas written down? Okay. So let's look at this first example. We're going to do this first one together. That might be a little small. I'll make it a little bigger. Woo! Now I'm telling you right now, it's going to be one of the three. So the first thing you're going to want to do is figure out which one of the three it is. And actually, if you look at it, I mean, we've seen problems that look kind of like this before, haven't we? This is where it's going to start getting a little, I don't know if tricky is the right word, but it's going to be like, wait, how do I know which one to use when? Don't worry about that so much today. That's one of the reasons why I'm spending 2 days on this. Today, I just want you to get used to using the formulas. But I'm telling you right now, it's one of those three, so which one do you think it is? Rena. Say it again. Yeah. How do you know it's arcsine? Yeah. Constant minus the variable. That's the key in the words are hard. In the integrand. So yes. So we want to keep this formula on the brain. Any questions why we're going to use arcsine? So now that we know we're going to use arcsine, it's kind of use substitution, but kind of not. What we want to do is we want to identify the U and the A in the formula. And you don't necessarily have to substitute in. Sometimes it helps. It's kind of a personal preference. Anyway, let me show you what I mean. So comparing what we have to the formula that I have on the right-hand side, can anybody tell me what does U equal in this formula? Trey. U is not 4x. You're on the right track, but you made it silly. Mason. 2x. Exactly. Because remember, I can think of this as 2x, 1 minus 2x squared inside the radical. Okay, so U is 2x. What is du then? And this is just like U substitution at this point. So Rena? Yeah. 2dx. And then the last thing that we want to spot is A. What does A equal in this problem? Yo, Jay. Yeah. Because it's like a 1 squared. So take a look at the problem and take a look at the formula. In the bottom, we're supposed to have a squared minus u squared. And we have a squared minus u squared. That's a match. That's perfect. In the numerator, we should have du. Do we have du? We're close, though, aren't we? I mean, I could take this dx and just move it in the numerator, and then du is 2dx. We have 3dx. So we're close, but not quite. So the easiest thing is just to actually do this. I'm going to move the 3 out, keep the dx there. So right now I haven't changed the problem, but we're going to do something similar to what we have seen in the past. I'm going to put a 2 there so that I have du. But if I multiply by 2, I also have to divide by 2 to keep it consistent. So any questions what I did there? Because now it's a perfect match. Now this part is optional. You don't have to do this, but in the beginning especially, it might help some of you guys. So I'm going to put a little optional here. Is to actually do all the substitution to see that you have what you want. So we still have the 3/2 on the outside. The 2dx is du, so I'm going to replace the numerator with du. If a is 1, then I can rewrite 1 squared as a squared. And then I have minus. And if u is 2x, then I can write 2x squared as u squared. And now you can see it's a perfect match for our formula. We just have that 3/2. But you don't really have to do that if you don't want to. If you remember the formula, you can just go to plug in your answer now. I'm going to go back to green. Anybody think they know what our answer is before I give it away? Rena? Perfect. That's exactly it. Now that you have that dead match for the formula, you can just fill into the formula. Arcsine of u over a, but you already know u over a is 2x over 1. Boom. And then obviously on this one, we can just write it as arcsine of 2x. And that's it. So you just want to rewrite it so that in the radical you've got a squared minus u squared, and that you have du on the top. That's it. And then if I go back to the formulas, The other ones are going to work very similarly. This guy right here, arctan, you're just going to want to rewrite it so that you have a squared plus u squared in the bottom and du on the top. And then for arcsecant, you're going to want to rewrite it so in the radical, it's u squared minus a squared. Make sure you got u on the outside though. Sometimes you have to play around to get the u on the outside. And then du on the top. Any questions? Because what I want you guys to try, give these a shot. At some point we'll stop and take a look at the first one, but just try these three right now. And then we'll come back. Here's a question answer to number 3. All right, anybody have any questions before we? All right, then. Number 4. Now, number 4 was sneaky because it actually doesn't use any of those formulas. It does, but it doesn't. It doesn't use our integration formulas. It actually uses the derivative formulas. This is where knowing those formulas fluently really helps you to see this. We have an arc cosine that's appeared from somewhere. Do we have the derivative of arc cosine in the problem? And we do. We're off by the negative, but we do. We have the 1 over the square root. So now this is our traditional u substitution. If I let u equal arc cosine, then here's du. Like I said, we just don't have the negative, so I just move the negative over. And how do you see that? Well, because I get that, like, how do we know when to use what? Part of it is just practice. You get to see different things. And honestly, part of it is knowing those formulas fluently. Because if you know them fluently, then it just kind of jumps out at you. Oh, I have an arc cosine, and I have the derivative of arc cosine in the problem. Remember, anytime you see the derivative of part of the problem in the other part of the problem, that's a good sign u substitution is going to work. I wouldn't say it works 100% of the time, but it's going to work 90% of the time. I've calculated it. It's exactly 90%. Made that up. Yo, Jay.
Ask you a question. So can I like cosine up and bottom?
Can you cosine up and bottom?
So I do cosine and then in parentheses I cosine square root.
I don't understand. What do you want me to write?
Like, so integral of cosine in parentheses r cosine x over cosine
The square root?
Will that work? I don't know. I did not got an answer on that.
It won't work because the cosines wouldn't cancel out in this case because they're not factors. You're not multiplying by cosine in the top and the bottom.
Yeah, like our cosine and our cosine were like onto each other. So the top would be x over cosine.
Yeah, but that's not equivalent to the original one. Yeah. All right, any other questions on these? Because I do want to do some more problems together, but we're going to do these together now because all of them introduce something kind of, they have their own twist. Does anybody still need this one, though, before I scroll? Okay. Are there any good movies coming out? Or came out? Mario? What is? Sonic 2? Didn't they just come out with Sonic 1? Really? It was that long ago? Man, I'm so out of it. Was the first one any good? Would I waste my time if I went and saw if I saw the first one? Nobody's answering. Okay. What? Which one is that one? Oh, that's the Marvel one, right? Yeah. Is it Marvel? Why do I? Oh no, I'm thinking Moon Knight. What's Moonfall? That sounds familiar too, though. It is a Marvel show? Okay. Is it already out? I gotta check. I'm like so far behind. All right, anybody still need this one? Okay. All right, guys, here's our next one. Write it down. Sorry, I think when I wrote these down ahead of time, it didn't look so small. So does this look like any of the formulas I gave you? Not really, right? I mean, I guess there's no square root, so possibly arctan, but I mean, if I just didn't have this 4x, then we could say x squared plus 13. U is x, a is root 13, right? But I do have the plus 4x, so I can't just do that. Anybody have an idea what I can do, Rena? Something to do, it's not with the quadratic formula, but you might be thinking along the right lines. Luca?
Is A 9 and U x minus 2?
You're very, 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 very close. I think you're so close, I think you did the right thing. You just, there was a little tiny twist. What did you do to get that?
I thought of so x squared or x plus 2. Is x squared plus 2 is x squared plus 4x plus 4, and then that leaves 9.
Yes, and you fixed the little tiny thing. You're exactly right. Complete the square. What? So I'm going to just off to the side here. Actually, here, let me write I'm completing the square. Complete the square. If you have x squared plus 4x, just start with that part. Well, here, actually, let me write the original. Godzilla. So we got x squared plus 4x. Now, if I'm going to just complete the square, what do I add to x squared plus 4x to complete the square? 4. Half of b squared. Half of 4 is 2, and 2 squared is 4. But I need to keep it equivalent to what I had. So what else do I need to keep it equivalent to plus 13? I need the plus 9. And then this part is x plus 2 squared. And the 9, for our purposes, we're going to want to think about what's squared. So I'm just going to rewrite it as 3 squared. And voila, we have what we want. So if I go back in here and just fill in that denominator with x plus 2 squared plus 3 squared. Now do you see the arctan hiding in there? So completing the square is a trick that we can use. Go ahead and try to finish it up now that you see that. Here's the answer up here. So completing the square, that's a sneaky trick we can do. Any questions about that? Yes. Mm-hmm. Anybody still need more time with this one? All right, here's our next one. So let's look at this one. This one also has a sneaky trick. Now this looks somewhat similar to our last problem, doesn't it? Well, I mean, we can still complete the square on the bottom. It's the numerator that's messing things up this time. Because we don't just have a constant up there, we have a 2x minus 5. So, what can we do? Rena. Factor it out? We can't do that because of the variable. We could factor out a constant, but we can't factor out a variable from the integral. So, Ruth.
Could you add in x and the next in the denominator? To get the derivative as 2x minus 5?
You're on the right track, but you said add and subtract 7x?
Yes.
You're on the right track, but not that. So here's what we're going to do, because I think you're thinking along the right things. Remember, this actually is kind of reminiscent of our natural logs that we've been doing. What's the derivative of the bottom? 2x plus 2. And remember, if we had the derivative of the bottom in the top, it should be a natural log problem. Now, we don't. We do have the 2x, so that's good. And we're not just off by a factor of a constant, though. This should say plus 2, but it says minus 5 right now. Well, let's just make it say plus 2. But of course, I need to keep it equivalent. So if I rewrite it this way, what do I still need to add or subtract to make it equivalent to the numerator I started with? I need a minus 7. And the reason why that's helpful, if you don't see it, is now I can split up this problem into two different integrals. I can have the integral of 2x plus 2 over the denominator, and then minus the integral of 7 over the denominator. And now I just am going to use two different techniques on each integral. So any questions how I got here? And remember, the reason why I got here, because there's how I got here and why I got here. The reason why I did this was so this first numerator is the derivative of the bottom. The derivative of the bottom is in the top. So that means it's a natural log problem. And then this guy is just like the problem we did previously where you complete the square. So complete the square, and then it will be an arctan problem. So any questions on that? I'm going to let you guys go ahead and try to finish it up. I'll pause the video too. All right, there is the answer right there. The first integral was all set up. Since we had the derivative of the bottom and the top, we're just ready to go right into the natural log. This guy now we had to complete the square, and then we can do the arctan. And you do complete the square on arcsine and arcsecant too. We just haven't done that. Yes?
Do you need to absolute value in the outline?
That is a great question. So this right here, the absolute value, remember, if it's already always positive, you don't need the absolute value. Do we know that this is already positive? Yeah, Subrath is shaking his head, yeah. And there's actually something in the screen right now which is telling us it's always positive. Remember, this denominator can be rewritten like this. Something squared will never be negative. And if something not negative is added to something not negative, then you know that it's never going to be negative. So, yeah, you're right. You actually could leave it off here. Good eye. Any questions on this one? There's two more. The last problem I want to give you is a challenge. But you do have, if I remember right, I think there's one of these on your homework tonight. The last one. Not this next one. We have two more. I'm babbling. You ready for the next one? Let's do it. Let's look at this guy. Make that bigger too. You guys think about this one. I'm going to pause it. Just take a moment to think about it, but then we'll start working through it together. What do you think it is? Arcsine, arctangent, arcsecant? Rena? Why do you think arcsecant? Yeah, but it's minus 2x, huh? Huh. But I like that you're not paying attention to what's on the outside. Perfect. Marcus? I know. Which one is it, huh? Well, let's complete the square and see what we got. What do I have to add to the x squared plus 2x to complete the square? So I have x squared plus, minus 2x. Yeah. What do I add to complete the square right here in the radical? Yeah, and it's going to be plus 1. But to keep it equivalent to what I had, what do I have to also put on it? Yeah, I need a minus 1. To keep it equivalent to what I had in the beginning, completing the square, add 1, minus 1 keeps it equivalent. So then, inside we have x minus 1 squared minus 1 squared. And that's inside the radical. Now, do you see the arcsecant pretty clearly? Because now it's variable squared minus constant squared. So go ahead and finish it up. See what you get. looks the same. There's your answer right there. We actually had everything set up. The u is x minus 1, which we did have on the outside, so that's cool. We have the du, we have the a, we just plug into the formula. Don't forget the absolute value, though. You do need the absolute value in your answer. Any questions on that? Because I'm going to leave you with one more. And it's not going to look like anything, any of these at first. But trust me, it will. Does anybody need this still? So here's the last problem. He's kind of unassuming. Definitely doesn't look like any of these. Not even close. But I'm telling you right now what to use for your u substitution. Now the u substitution here gets a little tricky too. But just try the regular u substitution. And as you go through it, you should see something pop up. So I'm going to give you like 5 minutes to think about this, and then we'll look at the answer. So I shall pause the recording. So here's getting to this point, and then see if you can bring it on home. Aren't these fun? I actually do kind of like them. This is where the puzzle like really comes in now. Trying to figure out the different things you could do and which one to do. And I'll tell you, sometimes you try something and it doesn't work. And that's okay. Go back and try something else. It happens to all of us. Anybody been using any of the Quizlets to help them study? I would recommend it. Keep those formulas fresh in your brain. Anybody think they have the final answer? Marcus, what'd you get?
2 square root of x minus 2 minus 2 square root 3 arctan of square root 3x minus 6 over 3 plus c.
I lost track a little bit, but I think you got it. Once you do the integration just in terms of u, that should be fairly straightforward. But then you got to replace the u. Remember, you can't leave your answer in terms of u. And 3 over root 3, this is one of the reasons why we rationalize, especially with just simple old numbers, because sometimes it just becomes really nice like that. Is that what you said, Marcus? Do you remember? You had 6 root 3 over 3 though, right? Or 2, right? Or something like that. Ah. Any questions at all? Because this is the last problem. Here, while you're looking at that, I'll pass that down. And by the way, this homework packet, because we are spending 2 days on this section, this is your packet for the next 2 homeworks. And it even says homework 6C and 6D on the top. So definitely don't lose this one. Says I'm not giving you another. I'm going to stop it. Stop.